Okay, next section is 2.5, complex zeros and the fundamental theorem of algebra. We're going to learn a couple major theorems. We're going to learn about complex conjugate zeros, the fact with real number coefficients, and they'll help us to complete the story that we've been trying to tell about these polynomials. And we haven't dealt with the situation where we have complex numbers yet, so that's what we're doing today. The fundamental theorem of algebra says that a polynomial function of degree n has n complex zeros. Keep in mind, complex numbers are both the real numbers and non-real, right? Because complex numbers are all numbers. So basically, if you have a fourth degree polynomial, there's 4 complex zeros. A couple could be real, a couple could be non-real. You could have all non-real, you could have all real. It just depends on what the fourth degree polynomial looks like, right? So here's an example. If I graph this fourth degree polynomial and it looks like this, then it's got 4 real zeros. Okay? If I graph the fourth degree polynomial and it looks like this, it's got no real zeros, all imaginary. Okay? If I graph the polynomial, it looks like this, let's say, then it's got 2 real zeros and 2 imaginary. Okay? You get the idea. Linear factorization says that we can just write those out as linear factors. You don't need to know this theorem. I mean, you need to know how to use it, just not the name of it. And I'll do some examples and show you exactly what that means. Fundamental polynomial connections in the complex case, if x equals k is a solution or a root, then it's a zeroed function and factors x minus k, something you already know. Works for complex numbers as well. So here's an example. Here's this polynomial is a second degree polynomial that has no real zeros. It's got 2 imaginary. And those 2 imaginaries are 3i and negative 3i. Okay? So those are the zeros that they want us to identify. They also want the x-intercepts. I'm going to show you what this function is by foiling it out. X times x is x squared. The middle terms are going to cancel. And then I have negative 9i squared, which I squared is a negative 1, so it's really just x squared plus 9. So it's a quadratic that's been shifted up 9 units. So all the way up at 9 right here, it's a quadratic that opens up. It doesn't have any real zeros. These are the 2 imaginary zeros. And it says the x-intercepts. Well, there are no x-intercepts, right? There's a y-intercept at 9, but no x-intercepts. So this is the same thing as this, but this is factored. And we're going to obviously go this direction where we're going to find these, in fact, be able to factor them today. Complex conjugate zeros basically just says that if a plus bi is a zero of a function, then a minus bi is a zero of a function. And that's important. I'll do an example for you here. This says write a polynomial function with minimum degree in standard form with real coefficients. So if 3 minus I is a factor, then 3 plus I has to be a factor, because that's the conjugate, right? Change the sign in between the real part and the imaginary part. And if 2 plus 5i is a 0, then 2 minus 5i is a 0. So this has to be a 1, 2, 3, 4, 5th degree polynomial. And I know it takes a while to multiply this all out, but that's what it's asking us to do. One of the factors is x plus 3. Another factor is x minus 3 plus I, right? Because that's the 0. So I have to put that right there and do x minus to get the factor. And then another one is x minus 3 minus I. And you also have x minus the complex number 2 plus 5i. And you also have x minus the complex number 2 minus 5i. I know this is a lot of work to FOIL all this out, but unfortunately that's what we have to do. So, a lot of work to show for this one. I probably won't give you one that's long in the test, but maybe a 3rd degree would be reasonable. So anyways, let's multiply these out. Now, I believe the middle terms are going to cancel. So let's just do this. You get the first 2 here. We multiply these 2 out. You get x squared, and then the first x here will give you minus x times 2 minus 5i. And then the next one will give you minus x times 2 plus 5i. And the last ones multiplied together give you a positive 2 plus 5i times 2 minus 5i. You multiply the first and last, the double negatives cancel, and you end up getting this. So I've got to simplify this. It's x squared I'm going to distribute this, that's minus 2x. Distribute this, but these terms are going to cancel. This positive 5ix and this negative 5ix will cancel, so I won't even write it. Actually, I'll write the first one all out, and I'll get lazy after that. Plus 5xi. All right, and then the next one would be negative 2x and negative 5xi. And then here I got to factor these two things, but they're conjugates, so we know that the middle terms cancel, and we get 4 minus 25i squared. I squared is negative 1, so this turns into positive 25. Now I got to simplify this sum, so this 5xi and the negative 5xi cancel, so I get x squared minus 4x plus 29. That's what these two complex factors FOIL into when you FOIL them all out. Okay. I'm going to do the same thing for these two right here. All right, so now I'm doing these two right here. And then so it's x times x, which is x squared. I'm probably going to need some more room though, so if you don't mind, I'm going to do this one up here, just so I have more room. And then I'll move the answer down here. So I have x times x, which is x squared. Then I have x, so it'd be negative x times 3 minus I. And then it'd be x times this would be another negative x, but this time times 3 plus I. And then negative times negative gives me quantity 3 plus I times quantity 3 minus I. And I have to simplify this. So this is going to be x squared minus 3x. And it's going to cancel again. These i's are going to cancel. This negative x, this is going to be positive xi, and this is going to be negative xi. So those will end up canceling. So I'll go right to this term and do this negative 3x now. And then FOIL this out, which gives me 9 minus I squared, which is really just plus 1, which is 10. So it's x squared minus 6x plus 10. I don't need these parentheses. And then I still have, I'm sorry, I do need these parentheses. This is being multiplied now. And then I still have x plus 3. So there's a polynomial with real number coefficients. I could FOIL this out even more, and I'm going to do that because it does want it in standard form. I know this is a ton of work, but I'm going to start with these two trinomials, multiply them together, and get x to the fourth, and then minus 4x cubed plus 29x squared, and then negative 6x cubed plus 24x squared. And then 6 times 29 is 174, so it would be minus 174x. And then the 10 would be plus 10x squared minus 40x plus 290. I need to simplify all this now. So x to the fourth, that's the only one of those. X cubed, there. So that'd be negative 10x cubed. And then 29x squared is here. Here's another x squared, here's another x squared. So 29 minus 6 is 23, plus 10 is 33. Gets rid of the x squareds. Gotten rid of the x cubes. I need now x's. So there and there. That'd be negative 214. X. And then I also need the 290. Alright, and then I still have to multiply that by this factor x plus 3. Which, like I said, I won't give you one this long on a test, but I'm not done yet. I have to multiply this all out, which gives me x to the fifth plus negative 10x to the fourth plus 33x to the third minus 214x squared plus 290x plus, and now I'll multiply 3 through, so it's 3x to the fourth minus 30x cubed plus 90 9 x squared minus 214, minus 3 times 214 is 642 x plus 290 times 3 is 870. So once I simplify this is my final answer for my function that we wanted. So I am going to have to add these together, and that gives me a final answer of x to the 5th plus negative 7x to the 4th plus 3x cubed minus 115 x squared minus 352x plus 870. I realize that is an absurd amount of work to do a fifth degree polynomial. I'll try to make these a little shorter for the test, but we are going to have to multiply that out. That's a polynomial in standard form with real coefficients that has the original given zeros, which are these 5 zeros. Okay. The book also makes a statement which is true, and we should go over this. So every polynomial function with real coefficients can be written as a product of linear factors and irreducible quadratic factors, each with real coefficients. So we're going to do a lot of problems like that. Like for example, this one. Let's go ahead and factor this one as product of linear factors and irreducible quadratic factors. Once again, kind of a long one, but let's get the real zeros first by graphing this in Desmos. Okay, so we have 3 real zeros, -3, -1/3, and 3. So -3, +3, and -1/3 are our zeros. So I'm going to write out 3 factors right away from that. I've got x plus 3, x minus 3, and x plus 1/3, which you can actually write that as 3x plus 1. That way when you stick a -1/3, basically just multiply through by 3. Okay, we can always adjust our a value. 3x plus 1. Okay, so there's our linear factors. Now, obviously the last term is a quadratic. It's a 5th degree, and it's an irreducible quadratic. So what I'm going to do is I'm going to FOIL this out and use long division just because I think it'll be a little quicker. This turns into x squared minus 9, and then I'm going to FOIL that times 3x plus 1. So it ends up being 3x cubed plus x squared minus 27x minus 9. And I'm going to divide that into this to find out the quadratic that's left over. So I'm going to write this up here. And divide it into this long polynomial, 3x to the 5th plus x to the 4th minus 24x cubed minus 8x squared minus 27x minus 9, and I'm going to just do this long division. So what do I put up here to multiply by 3x cubed to get 3x to the 5th? That would be x squared. X squared times, this gives me 3x to the 5th. Follow through now. Gives me x to the 4th. Follow through. Negative 27x cubed. And then follow through and you get negative 9x squared. All right, subtract, and you get positive 3x cubed plus x squared. Now let's drop down the negative 27x and the negative 9. And I need to multiply through now by another number that gives me this. This should just be 1. Multiply by 1, and you get, let me do this in a different color. Multiply through by 1, you get exactly this, 3x cubed plus x squared minus 27x minus 9. When you subtract, you get a remainder of 0. So there's the irreducible quadratic. That is the complete factorization right here. If I just put x squared plus 1, that is the complete factorization of this. This is an irreducible quadratic. You cannot factor that anymore with the real numbers. So you've got a quadratic here, which actually, I'm sorry, x squared plus 1. This would be the linear fact. This would be the complete factorization because this one can be factored into those two. There's the 3 linear factors, 1 irreducible quadratic, and that's our final answer. All right, we'll do some practice problems from Wilbur and hopefully make this make sense.